For centuries, humanity has looked to the stars and wondered if we are alone in the cosmos. But a far stranger question has emerged in modern physics. What if our universe is just one of many? The idea of parallel universes, once the realm of science fiction and philosophy, is now being seriously considered by some of the greatest minds in cosmology and quantum mechanics. If the multiverse exists, it would mean that beyond the reality we experience, there are countless other versions of existence, each with different possibilities, different histories, and perhaps even different versions of ourselves. Some universes may be nearly identical to ours, differing only in the smallest quantum variations, while others could be governed by completely different physical laws, making them unrecognizable to anything we can comprehend. The evidence for a multiverse is not yet definitive, but there are tantalizing clues hidden in the deepest mysteries of physics. Quantum mechanics suggests that every possible outcome of a situation may play out in separate, branching realities, an idea known as the many worlds interpretation. Cosmic inflation theory proposes that new universes may be continuously forming, each one budding off from an infinite cosmic fabric. The bizarre behavior of black holes, the unexplained properties of dark matter, and even the strange alignments in the cosmic microwave background radiation all hint that our universe may not be alone. If the multiverse is real, it would change everything we know about reality, shattering the notion that our universe is a unique and self-contained entity. It would mean that there are infinite variations of existence, where every possible event that could happen does happen somewhere in another universe. But how could we ever prove such a theory? One of the greatest challenges in physics is that, by definition, other universes would exist beyond the limits of our own observable cosmos, making direct observation seemingly impossible. Scientists are exploring ways to test the idea, searching for cosmic imprints or anomalies that might indicate interactions between our universe and another. Some believe that black holes might be gateways to other universes, while others suggest that certain patterns in the distribution of galaxies could reveal the presence of parallel realities. If we could one day confirm the existence of the multiverse, it would force us to rethink our place in the cosmos and question the very nature of existence itself. Would our lives still have meaning if infinite versions of ourselves existed elsewhere, making different choices and living out alternative destinies? Would the laws of physics as we know them be nothing more than a local rule set, specific only to our own pocket of reality? The implications stretch beyond science and into the deepest philosophical questions about identity, consciousness, and free will. But perhaps the greatest mystery of all is whether we will ever have definitive proof, or if the multiverse will forever remain an idea just beyond the reach of human understanding. The pursuit of this question is what drives scientific discovery forward, pushing the boundaries of what we know and challenging us to think beyond the limits of our own universe. Whether the multiverse is real or not, the search for answers is a journey that forces us to confront the vastness of reality and the possibility that our universe is just one small piece of a much greater, unimaginable whole. From the dawn of civilization, humanity has gazed at the night sky in wonder, seeking to understand the nature of the universe. Ancient cultures crafted myths and legends to explain the celestial bodies, often believing the cosmos to be a finite structure ruled by divine forces. The earliest recorded attempts to systematize our understanding of the universe date back to the Babylonians and Greeks, whose early astronomical observations laid the foundation for scientific thought. The Babylonians meticulously recorded the motion of the planets and stars, creating rudimentary celestial maps that helped predict eclipses and planetary movements. Meanwhile, Greek philosophers such as Pythagoras and Parmenides speculated about the structure of reality itself, introducing the idea that the cosmos could be governed by mathematical principles rather than mere superstition. One of the most influential early models of the universe was the geocentric model, developed by Claudius Ptolemy in the 2nd century CE. This model placed the Earth at the center of the universe, with the sun, moon, planets, and stars orbiting it in complex circular paths. This idea persisted for over a millennium, reinforced by religious doctrine and philosophical thought. However, the Renaissance brought a radical shift in our understanding of the cosmos. Nicolaus Copernicus, in the 16th century, proposed the heliocentric model, which placed the Sunday at the center of the solar system. This groundbreaking idea directly challenged the prevailing geocentric view and laid the foundation for modern astronomy. The heliocentric model gained further support through the observations of Galileo Galilei, who used one of the first telescopes to study celestial bodies. Galileo's discoveries such as the moons of Jupiter, the phases of Venus, and the detailed surface of the Moon provided direct evidence that not all celestial bodies orbited the Earth. His work, however, was met with fierce resistance from the Catholic Church, which saw heliocentrism as a direct contradiction to religious teachings. Despite this, the idea continued to gain traction, particularly with the contributions of Johannes Kepler, who formulated the laws of planetary motion, and Isaac Newton, whose work on gravity and motion explained the forces governing celestial mechanics. By the 19th and early 20th centuries, advances in observational astronomy allowed scientists to move beyond the study of our solar system and begin probing the larger structure of the universe. The discovery of spectroscopy enabled astronomers to analyze the composition of stars, revealing that they were made of the same elements found on Earth. This was a profound realization, suggesting that the universe operated under the same fundamental laws everywhere. The development of photography further revolutionized astronomy, allowing for detailed records of the night sky that could be analyzed over time. A true milestone in cosmology came in the 20th century with Edwin Hubble's discovery that the universe was expanding. Using the Doppler effect, Hubble observed that distant galaxies were moving away from us, and the farther away they were, the faster they seemed to be receding. This observation led to the formulation of the Big Bang theory, which proposed that the universe originated from an incredibly hot and dense state approximately 13.8 billion years ago. The confirmation of the cosmic microwave background radiation, CMB, in 1964 by Arno Penzias and Robert Wilson further solidified this theory, providing direct evidence of the universe's early state. As our understanding of the cosmos deepened, so too did the realization that the observable universe is only a fraction of what may exist. The concept of the observable universe is based on the distance that light has been able to travel since the beginning of time. Given that the speed of light is finite, we can only see objects whose light has had enough time to reach us, setting a boundary on our view of the cosmos. This does not mean that the universe itself has a physical edge, or rather, it suggests that beyond this limit, there may be regions of space that we can never observe due to the constraints of light and cosmic expansion. Modern cosmology continues to push the boundaries of what we know, with concepts such as dark matter, dark energy, and the multiverse challenging our fundamental assumptions about reality. The discovery that the universe's expansion is accelerating due to dark energy suggests that there may be more to the structure of the cosmos than we currently understand. Meanwhile, the search for dark matter, an invisible substance that appears to make up most of the mass in the universe, remains one of the most pressing mysteries in astrophysics. The question of whether our universe is the only one is a natural extension of these discoveries. If space extends infinitely, or if cosmic inflation produces an endless number of separate universes, then we may only be able to perceive a tiny fraction of reality. Some physicists argue that quantum mechanics supports the idea of parallel universes, where every possible outcome of a quantum event plays out in a separate reality. Others believe that string theory, which suggests that space has additional hidden dimensions, could provide a framework for understanding how multiple universes might coexist. Despite these incredible advancements, humanity is still only at the beginning of its journey toward understanding the true nature of existence. The vastness of space and the complexity of physical laws suggest that there are still many mysteries left to uncover. As new technologies emerge, such as next-generation space telescopes and powerful particle accelerators, we may one day find definitive evidence that confirms or refutes the existence of a multiverse. Until then, we continue to explore, question, and push the limits of human knowledge, driven by the same curiosity that has guided us since the first humans looked up at the stars. The idea that we may live in a multiverse reality where countless parallel universes exist alongside our own is not just a scientific hypothesis, it is a concept that strikes at the very core of human curiosity and existential thought. It challenges everything we believe about reality, free will, and our place in the cosmos. The search for answers is not just an academic pursuit, it is a deeply personal and emotional journey that forces us to confront the vastness of the unknown. It is a question that has fascinated philosophers, scientists, and storytellers for centuries. What if the reality we know is just one of many? What if, somewhere out there, another version of you is living an entirely different life, making different choices, and experiencing a different fate? People should care about this, because it is not just a theoretical puzzleite, it is a question about what reality is and what it means to exist. The very idea of a multiverse suggests that the world we see and touch is only a tiny fraction of a much larger and more complex structure. If true, it could mean that our lives are both more significant and more insignificant than we ever imagined. On one hand, the existence of infinite universes could mean that every possible version of history has played out somewhere. Every choice you have ever made and every path you never took exists in some parallel world. On the other hand, it also means that our universe is not unique, that what we consider to be our reality is just one of an unimaginable number of possibilities. This can be both awe-inspiring and terrifying, as it forces us to reconsider whether anything we do truly matters in the grand scale of existence. The vast unknown has always been a source of both wonder and fear. The idea that space continues endlessly, with no final boundary, already stretches human comprehension. But the multiverse goes even further. It suggests that not only is space infinite, but that there are infinite versions of it, each governed by different circumstances, rules, and histories. Some universes may be eerily similar to our own, differing only by a single quantum fluctuation. Others may be wildly different, with physics so foreign to us that we would not even recognize them as reality. The notion that there could be other Earths, other versions of ourselves, or even entire alternate histories where fundamental aspects of reality have changed is something that deeply unsettles the human mind. It forces us to ask, if there are infinite versions of me, then who am I really? Am I unique, or am I just one of many? This paradox is what makes the multiverse so emotionally compelling. It is a concept that lies at the intersection of science and philosophy, touching on deep existential questions about fate, destiny, and free will. If the multiverse is real, then every choice we make is both significant and insignificant at the same time. Every decision we make is played out in infinite variations somewhere in another universe. Another version of you made a different choice, leading to an entirely different outcome. This means that, in one sense, nothing is ever truly lost. Every possibility exists somewhere. But in another sense, it raises the unsettling question of whether our choices matter at all, if they all exist in some form across the multiverse. The emotional impact of this idea is not just about personal identity, it extends to the fundamental nature of human civilization. If the multiverse exists, then what does that mean for history? Are there universes where great historical events never happened, where wars were avoided, or where humanity followed a completely different evolutionary path? Could there be a version of Earth where life never emerged at all? These questions force us to think about the fragility of our own existence, about how easily things could have been different, and about the sheer vastness of possibility in the cosmos. One of the most powerful emotional reactions to the idea of the multiverse is the fear of insignificance. Throughout history, humans have sought to find meaning in the universe, believing that we hold a special place in creation. But if the multiverse is real, then our universe is not unique, it is just one of an infinite number. This realization can be deeply unsettling. If there are countless other versions of you living different lives, then what makes this version special? If there are infinite Earths, then what makes our planet important? This feeling of cosmic insignificance is something that has long haunted astronomers and philosophers alike. The more we learn about the universe, the more we realize how small we truly are in the grand scheme of things. But at the same time, the multiverse can also be a source of hope and wonder. If there are infinite realities, then anything that can happen does happen somewhere. This means that somewhere in the multiverse, every dream you have ever had has come true. Somewhere, a version of you is living out the life you always wished for. Somewhere, the world is free from suffering and conflict. The multiverse suggests that possibility is endless, that reality is not bound by a single fate, but is instead a constantly evolving web of infinite outcomes. This can be an empowering thought. It means that the limitations we perceive in our world are not absolute, that somewhere, anything is possible. The emotional pull of the multiverse is also what makes it such a compelling idea in storytelling. Science fiction, mythology, and philosophy have long explored the concept of parallel realities, from ancient myths of otherworldly realms to modern stories about alternate dimensions and time travel. The reason these stories captivate us is because they speak to something fundamental in human nature, the desire to understand the unknown, to imagine what could have been, and to explore the idea that reality is far greater than what we perceive. Whether it is the idea of encountering another version of ourselves or the possibility of escaping into another world, the multiverse represents the ultimate frontier of the imagination. At its heart, the concept of parallel universes is about exploration, curiosity, and the endless pursuit of knowledge. It is about pushing the boundaries of what we think is possible, about questioning our most basic assumptions about reality, and about embracing the idea that there is always more to discover. Whether the multiverse is real or not, the very act of contemplating it expands our understanding of the universe and of ourselves. It forces us to think beyond the limits of our own existence, to consider possibilities that challenge everything we know, and to embrace the idea that the cosmos is far more mysterious, complex, and beautiful than we ever imagined. In the end, the multiverse is not just a scientific theory, it is a gateway to some of the deepest and most profound questions that humanity has ever asked. It is an idea that inspires awe, that sparks curiosity, and that challenges us to think beyond our everyday reality. Whether it fills us with fear or excitement, the multiverse reminds us that we are part of something much greater than ourselves, something vast, unknowable, and endlessly fascinating. And perhaps, in the grand expanse of infinite possibilities, that realization is what truly makes us unique. Imagine, for a moment, that everything you know, your life, your choices, your very existence is just one version of reality among countless others. What if, in another universe, you made a different decision that changed everything? What if another version of you is living a completely different life? If the multiverse exists, then every possible outcome of every event is playing out somewhere across an infinite number of parallel worlds. Does this idea excite you, or does it make you feel small in the vastness of possibilities? This mystery is not just a theoretical puzzle, it forces us to rethink everything we know about reality itself. If multiple universes exist, it means our own universe is just a tiny piece of a much larger cosmic structure, one that may be beyond our ability to ever fully comprehend. How do we define what is real if there are infinite versions of reality? Would you still be the same person if a version of you in another universe made a different choice? What does it mean for concepts like free will, fate, and identity? These are not just questions for scientists, they are questions that touch on the core of what it means to exist. The potential impact of discovering the multiverse would be profound. It would change our understanding of physics, philosophy, and even the way we think about life beyond Earth. If other universes exist, are some of them home to intelligent civilizations? Could we ever find a way to communicate with another universe? Some scientists believe that clues to the existence of parallel universes may already be hidden in the cosmic microwave background radiation, the afterglow of the Big Bang. Others suggest that black holes may be gateways to other realities, or that certain quantum effects we observe in experiments could be evidence of parallel universes interacting with our own. If we were able to prove the existence of the multiverse, it would be one of the greatest scientific breakthroughs in history, fundamentally altering our perception of space, time, and our place in the cosmos. But even if we can't yet prove it, discussing the idea of the multiverse is essential. It encourages us to think beyond our everyday experiences and to challenge the limits of human knowledge. What would it mean for religion and spirituality if there were infinite versions of reality? How would it change our moral and ethical beliefs? If every possibility is realized somewhere, does that mean that good and evil are just relative concepts, playing out in different ways across the multiverse? And how would it impact our understanding of life and death? If every possible version of you exists somewhere, does that mean you never truly end? Or is your experience of consciousness tied to just this one version of yourself? This is why your thoughts and perspectives matter. The concept of parallel universes is not just an idea for scientists in laboratories. It is a question that affects how we see ourselves, our choices, and our purpose. Do you think the multiverse is real? If so, what kind of universe do you think exists beyond our own? Would you want to know if another version of you was living a better or worse life? If you could visit another universe, would you? Or do you think our reality is unique, and that the idea of a multiverse is just speculation? Let's explore this question together. Share your thoughts, your theories, and your questions. The discussion about the multiverse is one that belongs to everyone, not just scientists. The more perspectives we bring into the conversation, the closer we get to understanding the greatest mystery of all. Do we truly live in just one universe, or are we part of something infinitely greater? The vastness of space stretches out endlessly in all directions, an unfathomable ocean of darkness speckled with the distant glow of billions of galaxies. Each of these galaxies, a swirling mass of stars, planets, and cosmic dust, is home to untold mysteries. Some are spiral-shaped, rotating gracefully like cosmic whirlpools, their arms stretching outward in elegant arcs of light. Others are elliptical, ancient and tightly packed, home to the oldest stars in the universe. Then there are irregular galaxies, chaotic in form, scattered remnants of cosmic collisions that have reshaped them over millions of years. Between these immense structures lie the great cosmic voids, vast and empty regions where almost no matter exists. These voids, stretching for hundreds of millions of light years, are some of the most mysterious and unexplored realms of the cosmos, raising questions about the very structure of space itself. But the universe is not only composed of what we can see. Hidden within this immense structure is something even stranger: dark matter. This invisible substance, making up roughly 85% of all matter in the universe, does not emit or absorb light, making it undetectable through traditional telescopes. Yet, we know it exists because of the way it bends light from distant galaxies and holds entire galaxy clusters together with its immense gravitational pull. Without dark matter, galaxies as we know them could not have formed. Their stars would not have been held in place, and the universe itself would be unrecognizable. Still, despite decades of research, no one has ever directly detected a single particle of dark matter, leaving its true nature one of the greatest unsolved mysteries of modern physics. Even more enigmatic is dark energy, the force responsible for the accelerating expansion of the universe. Unlike dark matter, which binds galaxies together, dark energy pushes them apart, stretching the very fabric of space itself. Scientists first discovered this phenomenon in the late 20th century, when they observed that distant supernovae were moving away from us at increasing speeds. This was an unexpected and unsettling revelation. Before this discovery, it was assumed that gravity would eventually slow the expansion of the universe, possibly even causing it to collapse in a big crunch. Instead, dark energy is driving galaxies apart faster and faster, suggesting that the ultimate fate of the universe may not be contraction, but an eternal expansion into cold, empty darkness. If dark energy continues its relentless push, the cosmos may one day become so vast that all galaxies will disappear from view, leaving only the cold remnants of dying stars. The minds unraveling these cosmic enigmas belong to some of the greatest thinkers of our time. One of the key figures in this exploration was Edwin Hubble, whose observations in the early 20th century revealed that galaxies were moving away from us, leading to the discovery that the universe is expanding. His work laid the foundation for the Big Bang Theory, fundamentally changing our understanding of cosmic origins. Then came Stephen Hawking, who revolutionized our understanding of black holes, showing that they are not just cosmic traps, but dynamic objects that emit radiation, slowly evaporating over time. Hawking's work suggested that black holes could play a crucial role in shaping the structure of the universe, possibly even connecting to other regions of spacetime. Another pioneer, Alan Guth, introduced the concept of cosmic inflation, proposing that in the earliest moments after the Big Bang, the universe expanded exponentially faster than the speed of light. This idea helped explain why the universe appears so uniform on large scales, and why we do not see massive variations in temperature and density across the cosmic microwave background radiation. If inflation occurred as Guth suggested, it may also mean that our universe is just one bubble among an infinite number of others, a key component of the multiverse theory. Meanwhile, researchers like Max Tegmark and Brian Greene have taken the concept of multiple universes further, developing models that suggest parallel realities may exist beyond the limits of our observation. Tegmark categorizes different types of multiverses, including those where physical laws differ entirely from our own, creating worlds that may be beyond human comprehension. Green, a leading proponent of string theory, has explored the possibility that hidden dimensions could explain the existence of multiple universes stacked like layers beyond our perception. The pursuit of these cosmic questions is not just an intellectual exercise, it is a journey into the deepest mysteries of existence. The more we uncover, the more we realize how much remains hidden. Space is not a simple void, but a dynamic, evolving entity, shaped by forces that we are only beginning to understand. The eerie silence of the cosmos, punctuated by the faint hum of radiation from the early universe, serves as a constant reminder of how little we truly know. Are we alone in this vast expanse, or do other intelligent beings gaze at their own night skies, wondering the same thing? If parallel universes exist, are they accessible, or are they forever beyond our reach? These questions ignite a profound sense of awe and curiosity. The universe is not just a collection of stars and galaxies, it is a grand, unfolding mystery, a cosmic puzzle that challenges the limits of human understanding. Every new discovery, from the detection of exoplanets to the mapping of distant galaxy clusters, brings us one step closer to answering the ultimate question: what is the true nature of reality? Whether we one day prove the existence of a multiverse, or find that our universe is unique, the search itself is what defines us. As long as there are mysteries left to solve, humanity will continue to look outward, driven by an unshakable desire to explore the unknown. Despite humanity's relentless pursuit of knowledge, the ultimate question of whether we live in a multiverse or whether our universe has an edge remains elusive. As we probe deeper into the cosmos, paradoxes emerge, contradictions surface, and fundamental barriers in physics reveal that we may never be able to definitively answer these questions. The deeper we go, the more we realize that the very structure of reality may prevent us from ever discovering what lies beyond. The conflict is not just scientific, it is a struggle between what we can observe and what we can imagine, between the limits of technology and the boundless expanse of theoretical physics. The more we uncover, the more we realize that the answers may be forever out of reach. One of the first clues that we may never find the true edge of the universe comes from the observable universe itself. Our ability to see the cosmos is limited by the speed of light and the age of the universe. Light from the farthest galaxies has traveled for billions of years to reach us, but beyond a certain distance, there has simply not been enough time for light to travel from those regions to Earth. This means that even if the universe has a boundary, we may never see it, not because it does not exist, but because the laws of physics impose a fundamental observational limit. The cosmic microwave background radiation, the faint glow left over from the Big Bang, marks the farthest point we can observe. Beyond that, space may continue indefinitely, or it may come to an abrupt end, but we will never be able to witness it directly. Adding to this mystery is the nature of cosmic inflation, the theory that in the first fraction of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This inflationary expansion means that parts of the universe that were once connected were rapidly pushed apart, potentially forever beyond our reach. If inflation is eternal, as some physicists suggest, then the multiverse may consist of countless bubble universes, each forming in its own isolated region of spacetime. If this is the case, the concept of an edge becomes meaningless because each universe is self-contained, with its own set of physical laws. If our universe is just one of many, then we may never interact with or even detect the others, leaving us in a cosmic bubble with no way to see beyond. This limitation is not just theoretical, it is reinforced by fundamental paradoxes in physics that suggest we may never fully understand what lies beyond our universe. One such paradox is the tension between general relativity and quantum mechanics. General relativity describes gravity and the structure of space-time on a cosmic scale, while quantum mechanics governs the bizarre and unpredictable behavior of particles on the smallest scales. These two theories, despite both being incredibly successful in their respective domains, are fundamentally incompatible when applied to extreme conditions, such as the singularity at the center of a black hole or the earliest moments of the universe. If we cannot even reconcile our two best theories of physics, how can we hope to answer the even greater question of whether our universe has an edge? Another major obstacle in our search for the edge of the universe is dark energy, the mysterious force driving the accelerated expansion of space. Unlike normal matter, which clumps together due to gravity, dark energy acts as a repulsive force, pushing galaxies apart faster and faster over time. If dark energy continues to dominate the fate of the universe, then eventually, the expansion will accelerate to such an extent that distant galaxies will recede beyond the limits of our observation. This means that even the regions of the cosmos that we can see today will one day disappear from view, making it impossible for future generations to study them. In this scenario, the observable universe is shrinking in relative terms, and any information about what lies beyond is being lost to us permanently. If there is an edge to the universe, it may be expanding so rapidly that we will never reach it, no matter how advanced our technology becomes. Compounding these challenges are the inherent limitations of our observational tools and scientific methods. Even our most powerful telescopes, such as the James Webb Space Telescope, are limited by the wavelengths of light they can detect and the clarity with which they can see distant objects. The farther we look into space, the more we are constrained by cosmic dust, gravitational lensing, and the fundamental blurring effect of the universe's expansion. No matter how advanced our instruments become, they will always be bound by the physics of light and the distortions of space-time. There may be phenomena beyond the observable universe that we will never detect simply because the signals can never reach us. The limitations of observation extend to particle physics, where experiments at the Large Hadron Collider, LHC, have provided glimpses into the fundamental structure of the universe, but have yet to uncover direct evidence of extra dimensions or other universes. Some theories suggest that parallel universes could interact with our own through gravity, but if these effects are too weak or too subtle to measure, we may never be able to confirm their existence. If the multiverse exists but remains entirely inaccessible to experimentation, does it remain a scientific concept, or does it become a philosophical one? The very definition of science is based on the ability to test and falsify theories. But if we can never test the existence of other universes, are we doomed to forever speculate without proof? Our understanding of the universe is constantly challenged by new discoveries that force us to reconsider our assumptions. The detection of gravitational waves, the identification of exoplanets in habitable zones, and the ongoing research into dark matter are all reshaping our knowledge of the cosmos. But with each new discovery, we are also faced with new questions. Are we only seeing a fraction of reality? Could there be hidden aspects of space-time that we have yet to uncover? The search for the edge of the universe may not be a quest for a physical boundary, but rather a search for a deeper understanding of the nature of space and time itself. Ultimately, the greatest challenge to finding the edge of the universe is not technological or even scientific, it is conceptual. Our understanding of reality is shaped by our experiences within this universe. But if there are other universes with different physical laws, different dimensions, or even different definitions of time, then we may not even have the proper framework to comprehend them. If space-time itself is an emergent property, as some quantum gravity theories suggest, then what we perceive as edges or boundaries may be illusions, artifacts of our limited perspective. The more we learn, the more we realize how much we do not know. The search for the edge of the universe is not just about mapping space, it is about pushing the limits of human understanding, about confronting the fact that some questions may never have definitive answers. But that does not mean the search is without meaning. The pursuit of knowledge, even when it leads to more questions than answers, is what drives scientific progress forward. Whether we find the edge of the universe or simply expand the boundaries of our ignorance, the journey itself is what defines us. The more we seek, the more we uncover, and perhaps, in the process, we will come to understand that the true edge of the universe is not a physical boundary, but the limit of our own perception. The question of whether the universe is infinite or finite has led to one of the greatest conflicts in modern cosmology, dividing scientists into competing schools of thought. On one side, some physicists argue that the universe extends forever, without any edge or boundary, while others contend that it is finite but unbounded, meaning that while it has a defined structure, it lacks a physical edge. This fundamental disagreement arises from the complex interplay between observational data, mathematical models, and the limits of human perception. The struggle to define what lies beyond our observable universe has led to tensions between theoretical physics and empirical science, forcing cosmologists to confront the possibility that some questions may never be answered. One of the biggest sources of conflict in this debate is the nature of space-time itself. According to general relativity, space can be curved, meaning that the universe could be finite in volume, but still without an actual edge, similar to how the surface of a sphere is finite but does not have a boundary. In this model, if one were to travel in a straight line for long enough, they might eventually end up back where they started. This concept suggests that the universe could be shaped like a higher dimensional hypersphere, where there is no definitive end, but rather a continuous loop. However, quantum mechanics and inflationary cosmology introduce alternative possibilities, complicating the picture. The theory of cosmic inflation, first proposed by Alan Guth, suggests that in the earliest moments of the universe, space expanded exponentially faster than the speed of light. This process, if eternal, could mean that new pocket universes are continuously being created, forming an ever-growing multiverse. If this interpretation is correct, then the observable universe is just one small part of a much larger reality, one that extends indefinitely. In this scenario, searching for an edge becomes meaningless because the universe is constantly producing new regions of space that are forever beyond our reach. This tension between a finite yet unbounded universe and an infinite multiverse is one of the key struggles in modern cosmology. The observable universe, which is limited by how far light has traveled since the Big Bang, provides a boundary of what we can see. However, just because we cannot see beyond a certain distance does not mean that nothing exists beyond it. Some scientists argue that assuming an edge is a mistake, as the universe may simply continue indefinitely beyond our observational limits. Others suggest that new physics may emerge at extreme distances, possibly revealing a hidden structure to the cosmos that remains undetectable with current technology. The clash between these ideas is further complicated by the limitations of observational evidence. While theoretical models suggest different possibilities, direct measurements of the universe's shape and structure remain inconclusive. Some studies of the cosmic microwave background radiation, CMB, suggest that the universe is flat on large scales, meaning it is likely infinite. However, anomalies in the CMB, such as unexplained temperature fluctuations, have led some physicists to speculate that we may be seeing hints of an underlying cosmic structure or even interactions with other universes. If such signals exist, they could provide the first empirical clues to the existence of a multiverse, but proving this definitively remains an enormous challenge. Another major conflict arises from the attempts to unify general relativity and quantum mechanics. General relativity works exceptionally well on cosmic scales, explaining the large-scale behavior of space-time and gravity. However, when applied to extreme conditions such as black holes or the very early universe, it breaks down, suggesting that a deeper theory is needed. Quantum mechanics, on the other hand, accurately describes the behavior of subatomic particles, but does not incorporate gravity. Some physicists believe that a quantum theory of gravity, such as string theory or loop quantum gravity, is necessary to fully understand the structure of space-time and determine whether the universe has an edge. One of the more radical proposals emerging from quantum gravity is the holographic principle, which suggests that the three-dimensional universe we experience may actually be a projection of information stored on a distant, lower dimensional boundary. If this is true, then what we perceive as the edge of the universe may not be a spatial boundary, but a fundamental limit to how information is processed in the cosmos. This idea has profound implications, as it challenges our very notion of what it means for something to be real. The disagreement over the nature of the universe's edge is not just a theoretical struggle, it has philosophical and existential implications as well. If the universe is infinite, then everything that could possibly happen must be happening somewhere. Every choice you have ever made, every path not taken, could exist in some distant region of space, played out by a version of you in another part of the cosmos. If the universe is finite, then we are living in a much smaller, contained reality, one that might one day be mapped and fully understood. Either scenario has profound consequences for how we think about our place in the cosmos, the nature of existence, and even the question of free will. Despite these competing theories, no single explanation has been universally accepted. The search for a final answer continues, with cosmologists designing new experiments, developing better telescopes, and exploring alternative mathematical frameworks to bridge the gaps in our understanding. Whether we eventually find an answer or discover that the truth is beyond our reach, one thing remains clear. The debate over the universe's edge is one of the most fundamental and exciting conflicts in modern science, pushing the boundaries of human knowledge and challenging us to rethink everything we thought we knew about reality. If the universe has no edge, then the implications for physics, cosmology, and human understanding are profound. The idea of an infinite or unbounded universe challenges many of our fundamental assumptions about the structure of reality, forcing us to reconsider the very nature of space, time, and existence itself. The conflict between competing theories about the universe's shape and boundaries has led to major philosophical and scientific questions that remain unresolved. If the universe is truly infinite, then the way we approach cosmology must change, requiring new physics that can account for an endless expanse of space and matter. More importantly, it forces us to confront existential questions about our place in an unimaginably vast cosmos. One of the most immediate consequences of an infinite universe is that it would fundamentally alter our understanding of physics. Many cosmological models are built on the assumption that the universe, while vast, is still finite in scope. If it turns out that the universe has no edge and extends indefinitely, then we must rethink how we describe the fabric of space-time. Current theories, including general relativity, work well in describing the observable universe, but they do not necessarily account for a cosmos without limits. If space-time is truly infinite, then concepts such as cosmic expansion, entropy, and even the fundamental laws of physics may require significant revision. Could there be variations in the laws of physics across an infinite universe? If the universe is infinite, is there a structure to it, or does it continue without pattern or repetition? These are questions that physicists have yet to answer. In an infinite universe, the idea of the multiverse gains even greater significance. If the universe extends forever, then it is statistically inevitable that regions of space will exist that are identical or nearly identical to our own. This is because, in an infinite system with finite building blocks, such as atoms, every possible configuration of matter must eventually repeat. This means that somewhere, at an unfathomable distance from us, there could be an exact copy of Earth, complete with a version of you, living a life almost identical to yours. This realization raises significant questions about identity, free will, and the uniqueness of individual experience. If every version of reality plays out somewhere, then what does it mean to say that one event truly happened? Are we just one version of an infinite series of realities, each differing only by the slightest variations? From a philosophical standpoint, the idea that the universe has no edge challenges our deeply ingrained human tendency to seek boundaries and limits. Throughout history, our understanding of the cosmos has expanded with each new discovery, from the geocentric model to the heliocentric model, to the realization that our galaxy is just one among billions. If space truly extends without end, then we are faced with a reality where there is no center, no ultimate vantage point, and no final boundary that contains everything. This can be deeply unsettling, as it removes any notion of a special or privileged place in the universe. However, it can also be inspiring. If the universe is infinite, then the possibilities for exploration, discovery, and the search for meaning are equally limitless. The lack of an edge to the universe also has profound implications for the ultimate fate of the cosmos. If space extends forever, then the expansion of the universe may continue indefinitely, with galaxies moving farther apart until they become permanently isolated from one another. This scenario, often called the heat death of the universe, suggests that as stars burn out and matter disperses, the cosmos will eventually become a vast, dark, and lifeless expanse. However, if the universe has no edge and no limit, then it is also possible that regions of space may evolve differently, potentially giving rise to new forms of matter, energy, or even entirely new universes within the greater structure of reality. The idea that the universe is eternally self-renewing, with no final end, challenges conventional ideas about cosmic cycles and the nature of time itself. One of the most pressing scientific challenges posed by an infinite universe is the need for new physics. Current models of the cosmos rely on measurable, observable phenomena, but an infinite universe introduces concepts that may never be directly tested or confirmed. If space extends forever, then our observable universe is just a tiny fraction of reality, meaning that many of our measurements may be incomplete or misleading. Dark matter and dark energy, for example, may behave differently in regions beyond what we can see, requiring modifications to our current theories. Similarly, quantum mechanics, which governs the smallest scales of reality, may need to be reinterpreted in a universe where infinite possibilities exist. Another major challenge is the question of testability. In science, a theory must be falsifiable, that is, it must be possible to design an experiment that could prove it wrong. However, if the universe is infinite, then many of the concepts we are trying to test may be forever beyond our observational reach. For example, if parallel universes exist in an infinite cosmos, but they are separated by distances so vast that no signal can ever travel between them, then can we ever truly know if they exist? If the universe has no edge, then does it even make sense to ask what lies beyond it? These questions highlight the difficulty of applying traditional scientific methods to problems of cosmic scale. Despite these challenges, the pursuit of understanding an infinite universe remains one of the most exciting frontiers in modern physics. Some scientists believe that the answer may lie in mathematics and theoretical models, rather than direct observation. String theory, for example, suggests that space may have additional dimensions beyond the three we experience, and that these dimensions could help explain why the universe behaves the way it does. Others look to the holographic principle, which proposes that the universe as we perceive it may be a projection of information stored on a distant cosmic boundary. If this is true, then the question of whether the universe has an edge may be irrelevant, or reality may be defined not by physical boundaries, but by the way information is structured at the most fundamental level. Perhaps the most profound consequence of this conflict is the realization that human understanding will always be limited. No matter how advanced our technology becomes, there will always be aspects of the universe that remain beyond our reach. But rather than being a limitation, this is what makes science so compelling. The search for the universe's edge, or the realization that there may not be one, is a journey that forces us to rethink our assumptions, develop new tools, and expand our imagination. Even if we never find a final answer, the pursuit of knowledge is what defines us as a species. In the end, whether the universe has an edge or extends forever, the implications are staggering. If there is no edge, then we must accept that space is truly infinite, with all the paradoxes and possibilities that entails. If there is an edge, then we are faced with even greater questions. What lies beyond it, and why is our universe confined? Either way, the search for answers will continue, driven by our innate curiosity and the desire to understand the deepest mysteries of existence. And perhaps, in the process, we will discover that the ultimate answer is not about where the universe ends, but about how we choose to explore the limitless possibilities it presents. The search for the structure and limits of the universe has reached a critical turning point, driven by groundbreaking scientific revelations, advances in technology, and unexpected discoveries that have forced cosmologists to rethink their understanding of space, time, and the very fabric of reality. The question of whether the universe has an edge or extends infinitely has persisted for centuries, but recent developments in physics and astronomy suggest that we may be closer than ever to answering this profound mystery. New data from space telescopes, the growing influence of dark energy, and theoretical breakthroughs in quantum mechanics and relativity have dramatically shifted the conversation, leading to fresh insights that could redefine everything we know about the cosmos. One of the most significant turning points in modern cosmology came with the discovery that the universe is expanding at an accelerating rate, a revelation that fundamentally changed our perception of cosmic evolution. Before this discovery, scientists had assumed that gravity would eventually slow down the expansion of the universe, potentially leading to a reversal, a big crunch, or a gradual stagnation. However, in the late 1990s, astronomers studying distant supernovae found that galaxies were actually moving away from each other at increasing speeds. This unexpected acceleration could not be explained by existing models of gravity and matter alone, leading to the introduction of dark energy, mysterious force that appears to be pushing space apart at an ever-increasing rate. Dark energy, now accounts for roughly 70% of the total energy content of the universe, making it one of the most dominant, yet poorly understood components of the cosmos. The role of dark energy in shaping cosmic expansion has had profound implications for our understanding of the universe's fate and structure. If the universe is infinite, then dark energy will continue stretching space indefinitely, making it impossible to ever reach a physical boundary. If the universe is finite but unbounded, then dark energy could cause space to curve in such a way that it loops back on itself, reinforcing the idea that there is no true edge. Alternatively, some models suggest that dark energy could eventually rip space apart entirely in a phenomenon known as the Big Rip, where galaxies, stars, planets, and even atomic structures are torn apart as space expands faster than the speed of light. The discovery of dark energy has raised more questions than answers, challenging physicists to develop new theories that integrate this force into the broader framework of cosmology. At the same time, technological advancements have been instrumental in pushing the boundaries of what we can observe and understand about the universe. The launch of the Hubble Space Telescope in 1990 revolutionized astronomy, providing deep field images that revealed galaxies billions of light years away, offering an unprecedented look at the early universe. More recently, the James Webb Space Telescope, JWST, has extended our vision even further, allowing scientists to study the formation of the first galaxies and investigate the atmospheres of exoplanets in unprecedented detail. The ability to observe objects from the cosmic dawn just a few 100 million years after the Big Bang has given scientists a clearer picture of how structure in the universe has evolved over time. One of the most surprising findings from space telescopes has been the detection of unexpected patterns in the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang that permeates the universe. Some anomalies in the CMB suggest the possibility of cosmic inflation extending beyond our observable horizon, potentially providing indirect evidence of parallel universes or hidden dimensions. Other studies have found large-scale structures that appear to defy the expected uniformity of the universe, leading some to speculate that our universe may have interacted with others in the distant past. If these anomalies can be confirmed and better understood, they could provide some of the first empirical hints that the universe is part of a much larger and more complex reality. Another major breakthrough has come from gravitational wave astronomy, which has opened up an entirely new way of observing the universe. The detection of gravitational waves ripples in space-time, caused by the collisions of black holes and neutron star showers, provided a unique window into the most extreme environments in the cosmos. As gravitational wave observatories like LIGO and Virgo continue to refine their measurements, scientists hope to use them to probe the structure of space-time itself, potentially revealing whether there are extra dimensions or hidden aspects of reality beyond what traditional telescopes can detect. In addition to space-based observations, advances in particle physics have played a crucial role in shaping our understanding of the universe's limits. Experiments at the Large Hadron Collider, LHC, have tested the fundamental building blocks of matter, searching for new particles that could provide clues about the nature of dark matter, extra dimensions, or the potential existence of other universes. While no direct evidence of parallel universes has yet been found, some theories suggest that certain high-energy interactions could leave subtle imprints that indicate the presence of unseen realities. As we stand at this turning point, the conflict between competing theories of the universe's structure remains unresolved. While inflationary cosmology suggests that space-time is infinite and continuously generating new regions beyond our observable reach, quantum gravity theories like string theory hint that space itself may be emergent from deeper underlying principles. Some physicists propose that the universe is shaped like a four-dimensional hypersphere, meaning that while it has no edge, it is still finite in size. Others argue that our universe may be part of a larger multiverse, where an infinite number of realities exist, each governed by its own set of physical laws. The most exciting aspect of these discoveries is that they challenge the very limits of human knowledge. If space truly extends forever, then we must accept that we may never fully map or understand it. If the universe is finite, but has no edge, then our very concept of boundaries and borders must be redefined. If the multiverse exists, then we are just one of countless possible realities, raising deep philosophical questions about the nature of existence and individuality. Ultimately, the turning point we have reached is not just about scientific discovery as it is about the evolution of human thought itself. As our understanding of the universe grows, so too does our ability to question the assumptions that have guided us for centuries. The search for the universe's edge, whether physical or conceptual, represents one of the most profound scientific journeys of all time. Whether we one day discover a definitive answer or find that the mystery only deepens, the pursuit of knowledge will continue to drive us forward, pushing the boundaries of what we know and redefining our place in the cosmos. The search for the edge of the universe, or the possibility of multiple universes, has led scientists to question whether we are even approaching the problem correctly. For centuries, human understanding of space and time has been shaped by classical physics, which treats the universe as a vast, three-dimensional expanse governed by the forces of gravity and motion. However, as we dive deeper into quantum mechanics, relativity, and emerging theories in fundamental physics, a new perspective is emerging that suggests our very notion of an edge, or boundary, may be flawed. Instead of thinking about the universe as a physical space that expands outward, some scientists propose that reality itself may be holographic, emergent, or fundamentally different from what we perceive. One of the most radical shifts in perspective comes from the holographic principle, an idea that suggests that the three-dimensional universe we experience might actually be a projection of information encoded on a two-dimensional surface. Originally proposed by Gerard T. Hooft and later developed by Leonard Susskind, the holographic principle emerged from studies of black holes. When a black hole absorbs matter, all of the information about that matter is seemingly lost within its event horizon. However, physicists have shown that the information may not actually be destroyed, but rather encoded on the black hole's surface in a lower dimensional form. This insight led to the idea that the entire universe could work the same way. What we perceive as three-dimensional space might just be a projection of information stored on a distant cosmic boundary. If the holographic principle is correct, then the concept of an edge to the universe becomes meaningless. The fundamental nature of reality would not be defined by physical distances, but by the way information is structured and processed. This means that asking whether the universe has a boundary could be as irrelevant as asking what lies beyond the edge of a video game screen. The space we experience may be a mathematical construct rather than an actual infinite expanse. This view challenges not just our understanding of cosmology, but the very framework of physics itself. It suggests that the laws governing the universe are not local, but encoded on a distant boundary, and what we experience is merely an emergent phenomenon. Another paradigm shift comes from quantum mechanics, which has fundamentally altered the way we think about reality. Classical physics assumes that objects have definite positions and states, but in the quantum world, particles exist in superpositions, meaning they can be in multiple states at once until observed. This principle has led to the many worlds interpretation, which suggests that every possible outcome of a quantum event actually occurs, branching into parallel universes. In this view, the universe does not have a single well-defined structure. Rather, it constantly splits into an infinite number of realities, each representing different versions of events. If this interpretation is correct, then our perception of space as a singular, coherent entity is an illusion. We are constantly navigating through a web of branching realities that we cannot directly perceive. The question of whether the universe has an edge might therefore be misguided, because reality itself may not be a singular, self-contained structure. Instead, what we call the universe might just be one layer of a vast multiversal network, with different versions of space-time coexisting in ways we cannot yet comprehend. This shift in perspective is also forcing scientists to reconsider the role of space-time itself. Traditionally, we have thought of space and time as fundamental, immutable properties of the universe. However, theories such as loop quantum gravity and string theory suggest that space-time may actually be emergent arising from deeper, microscopic processes, rather than existing as a fixed backdrop. In loop quantum gravity, space-time is composed of discrete units, much like pixels on a screen. This means that at the smallest scales, space itself may not be continuous but quantized, with a finite resolution. If space-time emerges from these fundamental units, then asking whether the universe has an edge may be like asking where the edge of a fluid is. It depends entirely on how you define it. String theory takes this even further by proposing that reality consists of multiple hidden dimensions beyond the three we experience. These extra dimensions, if they exist, could radically change our understanding of cosmic boundaries. Some models suggest that our universe is a brane floating in a higher dimensional space, meaning that what we perceive as our cosmic limits might actually be the result of our restricted perception of reality. If higher dimensions exist, then the edge of the universe may not be an endpoint, but rather a transition into another form of existence. This evolving perspective is reshaping scientific discussions in profound ways. Instead of debating whether the universe is finite or infinite in physical size, some researchers argue that we should focus on understanding the deeper mathematical structure of reality. The shift away from classical notions of space-time and toward information-based models is influencing how we interpret cosmic data, from the behavior of black holes to the patterns observed in the cosmic microwave background radiation. Scientists are beginning to ask, is space something that exists on its own, or is it a byproduct of quantum interactions? Does time flow independently, or is it simply a measure of changing information states? These questions are leading to a fundamental reassessment of what it means to exist within the universe. Perhaps the most exciting aspect of this shift in perspective is that it suggests entirely new ways of approaching the mysteries of the cosmos. If reality is fundamentally informational, then our ability to understand it may depend not on how far we can see into space, but on how deeply we can analyze the patterns within it. The next generation of physics may not be about building bigger telescopes or particle accelerators, but about finding new ways to interpret quantum data, detect higher dimensional interactions, and uncover the hidden structures that shape the universe. Ultimately, the search for an edge to the universe may turn out to be a misinterpretation of the true nature of reality. Instead of looking outward for a boundary, we may need to look inward, rethinking the very assumptions that frame our understanding of space and time. Whether through the holographic principle, quantum mechanics, or new physics yet to be discovered, one thing is clear: the deeper we look, the more we realize that the nature of the universe is far more mysterious and far more extraordinary than we ever imagined. The deeper we explore the nature of the universe, the more we find ourselves confronted with unexpected revelations, discoveries that defy long-held assumptions and force us to reconsider the very fabric of reality. In recent years, the study of cosmology has undergone a radical transformation, with emerging theories suggesting that our universe is not the singular, self-contained entity we once believed it to be. Instead, we may be living in just one of an infinite number of universes, or worse, our entire existence may be nothing more than an elaborate simulation. These groundbreaking ideas challenge not just the foundations of physics, but our deepest philosophical and existential beliefs about our place in the cosmos. The unexpected discovery. The universe is not alone. For centuries, scientists assumed that the universe was a singular entity, expanding outward from the Big Bang in an ever-growing bubble of space and time. However, new developments in inflationary cosmology suggest that this picture may be incomplete. The theory of eternal inflation, proposed by physicist Alan Guth and expanded upon by André Linde, posits that in the earliest moments after the Big Bang, space-time underwent a period of exponential expansion. According to this model, inflation did not stop everywhere at the same time. Instead, different regions of space continued to expand at different rates, leading to the formation of bubble universes, each with its own physical properties. This realization suggests that what we call the universe may be just one small part of an infinitely larger multiverse. The implications of this are staggering. If there are an infinite number of universes, then every possible variation of reality exists somewhere. There could be universes where the laws of physics are completely different, where time moves in reverse, or where entirely new forms of matter and energy emerge. Even more astonishing is the idea that some of these universes could be nearly identical to our own, differing only by small quantum fluctuations. This means that somewhere out there, an alternate version of you may be living a slightly different life, making different choices, or experiencing an entirely different version of history. The multiverse and its controversies. While the multiverse theory provides an elegant explanation for many of the mysteries in modern physics, it also raises significant questions. If there are an infinite number of universes, does that mean that every event that could possibly happen has already occurred somewhere? And if every possibility exists, does that mean our choices are meaningless? These questions challenge our understanding of free will, identity, and personal significance. One of the biggest criticisms of the multiverse theory is that it is inherently untestable. Because these other universes exist outside our observable reality, there is no direct way to confirm or refute their existence. Some physicists argue that this makes the theory more of a philosophical construct than a scientific hypothesis, while others suggest that new discoveries in quantum mechanics and gravitational waves may provide indirect evidence of multiversal interactions. But the surprises do not end there. In addition to the idea that we may be living in one of many universes, some scientists propose an even stranger possibility, that our reality itself may be an illusion. The simulation hypothesis. Are we living in a cosmic illusion? The simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that our universe is not a physical reality at all, but rather a highly advanced computer simulation. According to this theory, if a sufficiently advanced civilization had the computational power, it could create simulated worlds indistinguishable from reality. Given the exponential increase in computational technology, some theorists argue that it is statistically more likely that we are living in a simulation than in a base reality. This idea is not just speculation. There are scientific reasons to take it seriously. Some physicists have pointed out strange mathematical structures in the laws of physics, such as the fact that certain fundamental constants seem to be coded with precise values that allow for the existence of life. Others have noted that quantum mechanics behaves in ways eerily similar to digital processing, with particles existing in probabilistic states until observed much like how a computer renders an image only when it is being processed. If the simulation hypothesis is true, it would mean that everything we perceive, space, time, matter, could be nothing more than an elaborate illusion, a complex set of instructions being run on an incomprehensibly advanced system. This raises even deeper questions. Who or what created the simulation? Why was it created? And what happens if it is turned off? Some theorists have even suggested that unusual cosmic phenomena, such as fast radio bursts or unexplained quantum anomalies, could be glitches in the simulation errors in the system that hint at its artificial nature. Alternative cosmologies. Are we thinking about reality the wrong way? Beyond the multiverse and simulation theories, alternative cosmologies are emerging that suggest reality may be far stranger than we ever imagined. The holographic principle, for example, proposes that the universe, as we experience it, is actually a three-dimensional projection of information stored on a distant, two-dimensional boundary. If this is true, then space itself may be an illusion, and what we perceive as physical reality could be a form of encoded information interacting in higher dimensional space. Another alternative theory suggests that time itself may be an emergent property rather than a fundamental aspect of reality. Some physicists propose that our perception of time flowing in a linear fashion is a consequence of quantum processes rather than an intrinsic feature of the universe. If true, this could mean that past, present, and future all exist simultaneously, and that what we experience as reality is simply a limited view of a much larger, timeless structure, a deeper realization about our place in the cosmos. All of these groundbreaking discoveries force us to reconsider what it means to exist. If the universe is infinite, then our own lives are just one of countless versions playing out across an unfathomable expanse. If we are in a simulation, then our understanding of reality is based on an artificial construct designed for unknown purposes. If the holographic principle is correct, then everything we experience is simply encoded information rather than a tangible world. These ideas challenge not just our scientific understanding, but our personal and philosophical perspectives. Are we insignificant in the grand scale of infinite realities? Or are we unique because we are aware enough to ask these questions? If the universe is a simulation, does that mean we should live our lives differently, seeking meaning not in material reality, but in the pursuit of deeper understanding? Does the existence of infinite universes lessen the value of our own experiences, or does it make them more precious, knowing that this exact moment is just one of many possibilities. The unfinished story of the universe. Despite all of these unexpected twists, we are still far from definitive answers. The mysteries of the cosmos continue to unfold, with each new discovery leading to even greater questions. The search for the universe's edge, or the realization that such an edge may not exist, has taken us to the frontiers of human knowledge, from quantum mechanics to the structure of space-time itself. Whether we find that we are part of a multiverse, living in a simulation, or experiencing reality in ways we have yet to fully comprehend, one thing remains clear. The journey to understanding the cosmos is far from over. The universe, as we perceive it, may not be what it seems. The deeper we go, the stranger it becomes. And perhaps, that is the greatest mystery of all, not just what lies beyond, but the fact that we are even capable of asking these questions at all. As our understanding of the universe expands, so too do the challenges that stand in the way of unlocking its deepest mysteries. While recent breakthroughs in cosmology, quantum mechanics, and observational astronomy have provided glimpses into the vast and complex nature of reality, many fundamental questions remain unanswered. The search for the edge of the universe, the existence of the multiverse, and the very nature of space-time are all topics that demand new approaches, better technology, and a willingness to rethink some of our most basic assumptions. However, several major hurdles must first be overcome before we can make meaningful progress in answering these profound questions. The limitations of current observational technology. One of the biggest challenges facing cosmology today is the fundamental limitation of what we can observe. The observable universe is restricted by the speed of light. We can only see as far as light has had time to travel since the Big Bang, roughly 13.8 billion years. However, because the universe has been expanding during this time, the actual observable boundary is much farther, estimated at around 46 billion light-years in every direction. Beyond this horizon, light from distant galaxies has not yet had enough time to reach us, meaning that even if the universe is infinite, we will never be able to directly observe its full extent. Additionally, cosmic expansion plays a crucial role in this limitation. Due to the influence of dark energy, the universe is not just expanding, but doing so at an accelerating rate. This means that many galaxies that are visible today will eventually move beyond our observable reach, forever disappearing from view as their light is stretched and redshifted beyond detectability. If space continues expanding indefinitely, there will come a time when we can no longer study the structure of the distant universe, leaving us with only a shrinking window of accessible information. Furthermore, our current telescopic technology, while powerful, has its own constraints. Even the most advanced instruments, such as the James Webb Space Telescope, JWST, have limits on how far and how clearly they can see. JWST has revolutionized infrared astronomy, allowing us to peer deeper into the cosmos than ever before, but it still cannot directly observe what lies beyond the cosmic microwave background, CMB, the afterglow of the Big Bang. This barrier effectively prevents us from seeing any earlier phase of the universe through traditional light-based telescopes. The need for next-generation space missions. To break through these observational barriers, next-generation space missions are essential. Several proposed projects aim to push the boundaries of our observational reach and test theories that could confirm or refute the existence of the multiverse, the true shape of the universe, and the role of dark energy. Some of the most promising missions include the Nancy Grace Roman Space Telescope, set to launch in the late 2020s. This telescope will conduct wide-field surveys of the universe, helping to map the effects of dark matter and dark energy on cosmic structure. The Euclid mission launched in 2023, a European Space Agency project designed to study the distribution of galaxies and the influence of dark energy on cosmic expansion. The Cosmic Explorer and LISA, Laser Interferometer Space Antenna, these gravitational wave observatories will allow us to probe the universe in ways traditional telescopes cannot, detecting ripples in space-time caused by massive cosmic events such as merging black holes or interactions between different cosmic regions. The CMBS-4, Cosmic Microwave Background Stage 4 Experiment, a proposed mission that will study the faint temperature fluctuations in the CMB, potentially revealing hidden clues about the universe's inflationary past and possible interactions with other universes. Beyond these, hypothetical megaprojects, such as space-based interferometers or a gravitational lens array, could allow us to magnify distant objects far beyond current limits, effectively extending our ability to observe deeper into the cosmos. Unanswered questions, and the theoretical challenges ahead. Even with improved technology, the biggest challenges in cosmology may not be observational, but theoretical. The most pressing questions still lack definitive answers, and some may never be fully resolved. Among them, is the universe truly infinite, or does it just appear that way? Some theories suggest that while the universe seems boundless, it may have a curved or closed structure, meaning that if one were to travel far enough, they would eventually return to their starting point. However, proving this requires a level of observational reach that is currently impossible. Does the multiverse exist? And if so, can we ever test it? One of the most frustrating aspects of multiverse theories is that they may be inherently unobservable. If parallel universes exist in separate space-time bubbles, then their effects might be completely inaccessible to any experiment we could ever perform. However, some cosmologists hope that indirect evidence such as unexplained anomalies in the cosmic microwave background or gravitational wave signals could provide clues. What is dark matter, and how does it fit into the larger picture? Dark matter makes up around 85% of all matter in the universe, yet we have never detected it directly. If our universe is one of many, then dark matter could be a remnant of higher dimensional physics that only interacts weakly with our reality. Can we unify quantum mechanics and gravity? The search for a theory of everything remains one of the greatest challenges in physics. General relativity describes gravity on large scales, while quantum mechanics governs the subatomic world. However, these two frameworks remain incompatible. Some scientists believe that resolving this conflict could unlock the true nature of spacetime and help us understand whether the universe has an edge or is part of a larger structure. The role of AI and advanced computational models. With the sheer complexity of these problems, artificial intelligence and machine learning are becoming critical tools in modern cosmology. AI-driven models can analyze massive datasets from telescopes, detect patterns that human researchers might miss, and even simulate the evolution of the universe under different physical conditions. For example, neural networks are already being used to improve gravitational wave detection, helping to filter out noise and identify weak signals, simulate cosmic inflation scenarios, testing whether certain models predict observable signatures that could be detected, classify galaxies and cosmic structures more efficiently, improving our ability to map the universe. As AI technology continues to evolve, it may play a key role in solving some of the deepest problems in cosmology, allowing us to explore concepts that would otherwise be computationally impossible. Ethical and philosophical challenges. As we move into a future where theories like the multiverse or simulation hypothesis become more accepted, we must also consider the philosophical and ethical implications of our discoveries. If we confirm that our universe is just one of many, does that change the way we view our existence? If we prove that we are living in a simulation, does it alter the meaning of consciousness and free will? Some of these questions may be beyond the scope of science, requiring a deeper dialogue between physicists, philosophers, and theologians. A future of uncertainty and possibility. Despite these challenges, one thing is clear: the quest to understand the universe is far from over. Every time we solve one mystery, we uncover another, pushing the boundaries of human knowledge further. Whether the universe has an edge, whether we are part of a multiverse, or whether space and time themselves are emergent properties of a deeper reality, the search for answers is what defines us as a species. The future of cosmology will depend on a combination of technological innovation, theoretical breakthroughs, and perhaps even a complete shift in how we perceive reality. While some challenges may seem insurmountable, history has shown that science has a way of surprising us. Just as we once thought Earth was the center of the cosmos, only to discover the vastness of space, so too may we one day uncover truths that are beyond anything we can currently imagine. Until then, the search continues. The question of whether the universe has an edge, extends infinitely, or is part of a greater multiverse remains one of the most hotly debated topics in modern physics. As we stand at the cutting edge of cosmology, competing theories offer vastly different visions of the nature of space, time and existence itself. While some models suggest that the universe is infinite and unbounded, others propose that it is finite yet closed, or that we are simply one bubble universe in an ever-growing multiversal landscape. The challenge of unifying general relativity with quantum mechanics only deepens the mystery, forcing physicists to question whether we will ever truly find a boundary if the concept of a cosmic edge is fundamentally flawed. The latest competing theories and their strengths. Several competing theories have emerged, each offering a different answer to the question of the universe's structure and ultimate limits. While some rely on observational data, others are deeply rooted in theoretical physics. Point 1. The infinite universe hypothesis. One of the simplest yet most perplexing possibilities is that the universe extends forever, with no edge or boundary. This idea is supported by observations of the cosmic microwave background radiation, CMB, which suggests that the universe is geometrically flat on large scales. If the universe were curved in a way that suggested it was closed or finite, we would expect to see distortions in this ancient light, yet none have been observed. Strengths. This model aligns with Einstein's general relativity and is mathematically simple. Challenges. If the universe is infinite, then everything that can possibly happen must be happening somewhere, leading to bizarre implications for identity, consciousness, and even physics itself. 2. The finite but unbounded model. Another possibility is that the universe is finite in size but unbounded, meaning that space curves back on itself like the surface of a sphere or a torus. In this scenario, traveling in a straight line far enough in any direction would eventually bring you back to your starting point. Strengths. This model resolves the paradoxes of an infinite universe, while still explaining why we don't see an edge. Challenges. It is difficult to reconcile this model with the latest measurements of cosmic expansion and dark energy. 3. The multiverse hypothesis. If inflationary cosmology is correct, then our universe may be one of countless others, each forming in a vast multiversal landscape. Some theories, such as eternal inflation, suggest that new universes are continuously being created, each with its own physical properties. This could explain why our universe appears fine-tuned for life, because we exist in one of the rare regions where conditions are just right. Strengths. The multiverse model provides a possible solution to the fine-tuning problem, why the fundamental constants of physics appear precisely calibrated for life. Challenges. There is no direct way to test or observe other universes, making the multiverse theory highly speculative. 4. The holographic universe. An even more radical possibility is that the universe is not three-dimensional at all, but rather a holographic projection of information stored on a distant, lower-dimensional surface. This idea, known as the holographic principle, emerged from black hole physics and suggests that everything we experience is merely a projection from a deeper layer of reality. Strengths. This model could help bridge the gap between general relativity and quantum mechanics. Challenges. It is highly theoretical and difficult to test experimentally. The ongoing debate. Will we ever find a true boundary? Even if one of these models turns out to be correct, there remains an even deeper question. Will we ever find a true boundary to the universe? If the universe is infinite, then there may be no meaningful edge to discover. If it is finite but unbounded, then any attempt to reach a boundary would result in looping back to where we started. But what if the edge of the universe is not a physical limit, but a limit of perception? If the holographic principle is correct, then the boundary may be a fundamental limit to how much information can be processed, rather than a physical endpoint. Likewise, if space-time is emergent, then our understanding of cosmic boundaries may be entirely conceptual, rather than something that can be reached by travel or observation. The challenge is that our current scientific tools are fundamentally limited. We can only observe as far as light has had time to travel since the Big Bang, meaning that even if a true boundary exists, it could be billions or trillions of light years beyond what we can ever detect. If the universe is expanding at an accelerating rate, then the most distant regions may be moving away from us faster than the speed of light, making them permanently inaccessible. Unifying physics. The search for a theory of everything. One of the greatest barriers to resolving this debate is the failure to unify general relativity with quantum mechanics. These two theories describe different aspects of reality, yet they remain fundamentally incompatible. General relativity describes gravity and the structure of space-time on large scales, but it does not account for quantum effects. Quantum mechanics describes the behavior of particles at the smallest scales, but it breaks down when applied to gravity. Several approaches are being explored to unify these theories. String theory suggests that all particles and forces are composed of tiny vibrating strings in extra dimensions. If correct, string theory could explain why space-time behaves differently at different scales, and possibly provide insights into the nature of cosmic boundaries. Loop quantum gravity proposes that space-time itself is composed of discrete quanta, meaning that space is not continuous but exists in fundamental units. Causal set theory suggests that space-time is built from discrete elements, similar to a vast network of nodes and connections. If any of these theories prove correct, they could reshape our understanding of cosmic structure, revealing whether the universe has a definable boundary or if space-time itself is part of a deeper, hidden framework. The future of cosmology. Looking ahead, the future of cosmology will be shaped by new technological advancements and theoretical insights. The next generation of space missions, including the Nancy Grace Roman Space Telescope, gravitational wave observatories, and the Square Kilometre Array, will provide unprecedented data on the structure of the universe. Some of the key questions these missions will aim to answer include: what is the true geometry of space-time? Does dark energy behave differently in different parts of the universe? Can we detect gravitational signals from beyond our observable horizon? Is there direct evidence of extra dimensions or hidden layers of reality? As artificial intelligence and machine learning continue to revolutionize data analysis, scientists will also be able to process vast amounts of cosmic information more efficiently, uncovering hidden patterns and correlations that might offer clues to the fundamental nature of space and time. Conclusion: a universe without limits? The search for the edge of the universe is not just a scientific question, it is a philosophical and existential challenge. Whether the universe is infinite, finite but unbounded, or part of a multiversal system, the answer will fundamentally alter how we see ourselves in the grand scheme of existence. Perhaps the greatest realization of all is that there may not be a single answer to this question. The deeper we probe into the nature of reality, the more we find that space, time, and even existence itself are not as straightforward as they once seemed. Whether we find a true boundary or discover that the universe is forever unknowable, the search itself is what defines us. The final confrontation in this debate is not just about physics, it is about how far we are willing to push the limits of human knowledge. The cosmos may be endless, but so too is our desire to explore, to question, and to understand. And in the vast, infinite darkness of space, perhaps that curiosity is the one true constant. The search for the limits of the universe, whether it has an edge, extends infinitely, or exists as part of a greater multiverse, is more than just a scientific endeavor. It is a profound reflection of humanity's relentless curiosity and the pursuit of understanding. Throughout history, we have sought to push beyond the boundaries of what we know, exploring not just the physical world around us, but the very nature of existence itself. The deeper meaning of this journey goes far beyond mathematics and physics. It speaks to the core of what it means to be human. It reminds us that our place in the cosmos is not just about where we are, but about our ability to ask, to wonder, and to strive for knowledge despite the vast unknown that surrounds us. The deeper meaning of exploring the unknown. For centuries, humans have looked up at the night sky with awe and curiosity, wondering what lies beyond. This instinct, the need to explore, to question, to seek understanding, has driven every great leap in knowledge. From ancient civilizations mapping the stars to modern-day physicists searching for quantum truths, the desire to comprehend the unknown is one of the defining characteristics of our species. Exploring the universe is not just about discovering distant galaxies or solving mathematical equations. It is about understanding ourselves. Every breakthrough in cosmology, whether it be the realization that the Earth is not the center of the universe, the discovery of cosmic expansion, or the theory of the multiverse, has forced us to redefine our place in existence. These discoveries humble us, showing us that we are a small part of a vast, unfolding reality. Yet they also elevate us because even in our smallness, we are capable of comprehending the vastness of the cosmos. If the universe is infinite, if there is no edge, or if we exist as one reality among countless others, what does that say about our significance? Does it mean we are unimportant, or does it mean that our ability to search, to wonder, and to understand is what truly gives us meaning? The act of questioning itself is a testament to our intelligence, our resilience, and our boundless imagination. How curiosity drives scientific progress. Every major discovery in history began with curiosity. The desire to look beyond the immediate is what led humans to cross oceans, to build telescopes, and to develop quantum physics. If we did not question the unknown, we would never have left the caves, never have wondered about the motion of the planets, and never have explored the microscopic world of atoms. Curiosity is not just about seeking answers, it is about challenging assumptions. Many of the greatest scientific revolutions have come from realizing that what we thought was true was incomplete or even entirely wrong. The shift from a geocentric to a heliocentric universe, the realization that time is relative, the discovery that space is expanding, each of these breakthroughs happened because someone dared to ask, what if our understanding is wrong? And what else is out there? But curiosity also requires persistence. Many of the most significant discoveries have taken decades or even centuries to confirm. The search for the Higgs boson took 50 years. The detection of gravitational waves, predicted by Einstein in 1916, was not confirmed until a century later. The question of whether the universe has an edge or what lies beyond it may take generations to answer. And yet, the pursuit itself is valuable. Even when we do not find the answers we expect, we uncover new mysteries, new ideas, and new ways of thinking. The balance between knowledge and mystery. One of the most humbling aspects of cosmic exploration is that with every new discovery, new questions arise. The more we understand, the more we realize how much we do not know. This balance between knowledge and mystery is crucial not just in science, but in philosophy, spirituality, and human progress. There is a temptation to seek final answers, to want to believe that one day we will solve the universe like a mathematical equation. But history has shown that every time we think we have reached the ultimate truth, new discoveries force us to expand our perspective. The mystery is never ending, and perhaps that is a good thing. If we ever reached a point where there was nothing left to discover, what would drive us forward? Mystery is not a failure of science, it is the fuel of discovery. The unknown is what keeps us searching, keeps us questioning, and keeps us striving to push beyond our limits. If the universe has an edge, then what lies beyond it? If it does not, then what does that mean about the nature of reality? If parallel universes exist, then how do they interact with ours? Each question leads to another, and that is the beauty of the pursuit. Rather than seeing mystery as an obstacle, we should embrace it. It is a reminder that the universe is greater than our comprehension, that existence is filled with possibilities beyond our current understanding, and that there will always be something more to explore. Lessons humanity can learn from cosmic exploration. The search for the universe's edge or for the structure of reality itself teaches us lessons that extend far beyond science. The quest for knowledge mirrors many of the struggles and aspirations we face as individuals and as a civilization. Humility and perspective. Understanding the universe teaches us humility. We are a tiny part of an immense cosmos, and yet we are privileged to be able to comprehend even a fraction of it. It reminds us that our daily concerns, while important, exist within a much grander picture. It encourages us to look beyond ourselves, to think in longer timescales, and to appreciate the incredible reality in which we live. Collaboration over isolation. Cosmic exploration is not the work of one person, one nation, or one generation. It is a collective effort, requiring collaboration across cultures, disciplines, and centuries. The discoveries we make about the universe are universal, they belong to all of humanity. This serves as a powerful reminder that progress is best achieved together, through cooperation rather than division. The value of imagination. Many of the greatest scientific discoveries started as ideas that seemed impossible. The concept of black holes, the idea that time slows down under strong gravity, the existence of other planets outside our solar system were once thought to be fantasies. The study of the universe teaches us that imagination is just as important as logic, and that daring to think beyond the possible is what leads to revolutionary breakthroughs. Adaptability and growth, just as the universe is constantly expanding, so too must our understanding. Clinging to outdated ideas simply because they are comfortable limits progress. The history of science has shown that being willing to change one's perspective is essential. The ability to adapt to new information, to challenge old assumptions, and to grow intellectually is what drives humanity forward. Endless possibilities. Whether or not the universe has an edge, whether we live in one reality or many, the ultimate lesson is that existence is filled with possibilities. The mere fact that we can ask these questions, that we can imagine, theorize, and explore shows that we are part of something extraordinary. Whether the cosmos is infinite or not, the potential of the human mind is boundless. Conclusion: the journey itself is the answer. As much as we seek definitive answers about the universe, perhaps the greatest revelation is that the search itself is what matters most. Whether we one day prove that the universe is finite or infinite, whether we discover parallel realities, or confirm the nature of dark energy, the true value of this journey is not just in the answers, but in the process of exploration. The universe, with all its vastness and mystery, is an invitation to wonder, to question, to learn, and to grow. As long as we continue to explore, we are fulfilling our greatest potential as a species. And perhaps, in the grand expanse of space and time, the act of seeking itself is the most profound answer of all. The question of whether the universe has an edge, extends infinitely, or exists as part of a greater multiverse is not one that can be easily answered. The pursuit of this mystery has led us to some of the most profound discoveries in cosmology, from the realization that the universe is expanding to the possibility that reality itself may be a holographic projection. Yet, despite these advancements, the fundamental nature of the cosmos remains unresolved. Should we continue searching for a definitive answer, or is there value in accepting that some questions may never be fully answered? Should we seek closure, or embrace the mystery? The case for an open-ended mystery. One of the greatest strengths of science is that it does not require absolute certainty to be meaningful. The pursuit of knowledge is valuable in and of itself, and often, the questions we ask are just as important as the answers we find. The search for the edge of the universe, or for the structure of reality, may never yield a final, definitive conclusion, but that does not mean it is without purpose. Each new discovery brings new insights, opens new avenues of exploration, and forces us to refine our understanding of the universe. Leaving the mystery open-ended allows for continual progress. If we were to claim that we had definitively solved the question of the universe's structure, we might close ourselves off to new possibilities. Historically, many final scientific conclusions have later been overturned. At one point, it was believed that the Milky Way was the entire universe, that time was absolute, and that space was static. Each of these ideas was eventually replaced by deeper, more accurate models. By keeping the question of the universe's nature open-ended, we allow for the flexibility necessary for future discoveries. Furthermore, mystery itself has intrinsic value. The unknown is what drives human curiosity, creativity, and innovation. If there were no mysteries left to solve, what would push us to explore further? The universe's vastness, its paradoxes, and its unanswered questions are what make the search so compelling. The possibility that there may always be more to learn ensures that we remain engaged, questioning, and striving for deeper understanding. The value of leaving questions unanswered. Not every question requires an answer to be valuable. Some of the most profound concepts in philosophy, science, and human thought are meaningful precisely because they invite contemplation rather than provide resolution. The search for the universe's edge, or for the fundamental structure of reality, forces us to confront deeper questions about existence, meaning, and our place in the cosmos. If the universe has no edge, what does that mean for our perception of boundaries and limits? If we are part of a multiverse, how does that change our understanding of uniqueness and individuality? If space itself is an emergent property rather than a fundamental aspect of reality, what does that say about the nature of existence? These are not just scientific questions, they are existential and philosophical inquiries that challenge how we define reality itself. Moreover, some questions may be unanswerable within the limits of human cognition and technology. Just as a two-dimensional being living on a flat surface might struggle to comprehend the concept of depth, there may be aspects of reality that are simply beyond our current or even future understanding. If the universe is shaped by principles that we have yet to discover, if its structure is fundamentally beyond our perception, then searching for a definitive conclusion may be an exercise in futility. Accepting that some aspects of reality may always remain unknown is not a failure of science, but rather an acknowledgement of its true nature, an evolving, ever-deepening process of discovery. Summary of the biggest takeaways. Looking back at our exploration of the universe's structure, several key themes emerge. The universe is vast and mysterious. Whether infinite or finite, the universe is far beyond the limits of human experience. The observable universe is only a fraction of what may exist beyond our reach. Competing theories offer different visions of reality. Some models suggest an infinite cosmos, while others propose a closed but unbounded structure. The multiverse hypothesis presents the possibility that we are just one of many universes. The holographic principle suggests that our perception of space may be an illusion. Technology and science continue to push boundaries. Space telescopes, gravitational wave observatories, and quantum experiments are expanding our understanding. Advances in AI and computational physics may provide new ways to analyze cosmic data. Mystery fuels discovery. The unknown drives human curiosity and scientific progress. Every new answer leads to more questions, ensuring that exploration never truly ends. Existence is a grand puzzle. The search for the universe's structure is not just about physics, it is about our place in the cosmos. Whether the universe has an edge or not, the mere act of questioning it gives meaning to our pursuit of knowledge. Final thoughts on the infinite possibilities of space. The nature of the universe, whether finite or infinite, remains one of the greatest unsolved mysteries of all time. But perhaps the journey itself is the answer. The act of searching, questioning, and pushing the boundaries of human knowledge is what makes us explorers, scientists, and thinkers. If we ever do find a definitive answer, it will likely open up even greater questions. That is the nature of discovery. Every horizon we reach only reveals a wider expanse beyond. Whether we ultimately prove that the universe is boundless, finite but unbounded, or part of a greater multiversal structure, the process of seeking these answers defines us as a species. In the end, should we seek an open or closed conclusion, perhaps the best answer is both. We should pursue knowledge relentlessly, embracing every new discovery, while also recognizing that the mystery itself is a fundamental part of the beauty of the cosmos. It is the questions, not just the answers, that make the universe so endlessly fascinating. So, as we continue to explore, we should embrace both the known and the unknown, understanding that the edge of the universe, if it exists at Alice, not just a physical boundary, but a symbol of the limitless potential of human curiosity. And that is a mystery worth preserving.